Is about capacitors. A quick rundown of what a capacitor is. This is the circuit symbol for one, and if electrons are coming up here, you will notice that they're going to build up on one side of the plate, and this is charging. Because there is space in between, it's insulated, they cannot cross. So that means the electrons are getting stuck on one side, building up over time. If that's happening, the electrons here are being repelled, which means that's left with only the positive charges. Now we have a charged plate. As long as that there is a voltage applied and it is having current, you can disconnect it afterwards and you will have the electrons stuck on the plate. And then you can plug it into a circuit, close the switch, and it will discharge. So the plan is we're going to understand and calculate the voltage over time, the charge over time, and we will even know about the current as well over the time when it's charging and discharging. So for a circuit which has a capacitor, we need to have something called an RC circuit, a resistor and a capacitor. So this is how it would typically look like. You have your battery, you have a switch, ammeter, voltmeter just to check, and then you have your resistor which controls the current, and then your capacitor which holds the current on the plate. Okay, and if you were to make a little graph, it is charging, it will slowly build up, and then it will tail off until it gets to the end. So the reason, again, why we have a resistor is to control the current. We don't want to have an infinite current causing problems. And two factors that will affect how it charges: the size of the capacitor. Of course, a bigger capacitor will take longer to charge, and the size of the resistor. The stronger resistor will slow the current down more, which will take, again, longer to charge. So having three different resistors, you can notice that you have three different times it takes to get to the maximum charge, like this. Very nice. So the discharge graph will be the opposite. It's going to be an exponential decay graph. It's going to be coming down because I'm losing the voltage. Okay, so this is the charging graph. This is the discharging graph. Current will be the same. It is for charging. Because the capacitor is holding on to the current, in the whole circuit the current is reducing until the capacitor is full. When the capacitor is full, of course, the current cannot flow because they're stuck, right? Discharging is different. Discharging is, this is 0 and this is now on the negative side. Why does it look like this? Well, what's happening is once you discharge it, the electrons will go back the way they came from. So if I had a plate like this and I had electrons going towards the left and they're building up over here, once I connect it to a circuit, they will actually discharge, and they cannot keep going left because, remember, there's a gap. They have to go in the opposite direction, which is why it's negative. And assuming there is no battery or anything to keep them going, they will slowly stop until they run out of energy, and then the electrons will stop flowing. Capacitor is fully discharged. So as we know, increasing the resistance increases the time taken. Increasing the capacitor increases the time taken. Again, less current will flow if you increase the resistance, as you know from the rule, Ohm's law. Bigger R, smaller I. Increasing the capacitance will increase the time because it can store more charge, so it will take longer to charge. Okay, so when you turn the switch on, the capacitor will fully charge. It will start to charge. It takes time, but it will get there. If we apply Kirchhoff's voltage law into this, we have a loop over here. This part is not too important to understand because this is going to take us to the formula. The formula is the important part, but I'll run through it anyway. So we have a positive voltage here, a negative here, and a negative here. We know that we have the voltage, negative Q over C. If you remember the rule, Q equals CV, just rearranging because V equals Q over C. This is from the capacitance rule that we know from before, Q equals CV, right? So we'll just rearrange to get this. So I substitute Q over C in here. And the same thing, we can substitute V equals IR into here. And instead of saying I, because we don't know I, we can do Q over T, which is quit. So we're going to take V equals IR. And instead of I, we know quit, Q equals IT. So I'll say I equals Q over T. So we'll do Q over T multiplied by R. That's how you get to here. Nice little integral solution you can get, and you will end up with this final answer. The Q, the charge at any time on this capacitor, is equal to the total charge possible multiplied by the time it will take to get there. 1 minus e to the negative t over RC. Okay, so this final total charge, we know we can just use Q equals CV. We can just bring that back to find the total. So you can write the formula as Q equal Q full or Q final multiplied by this extra piece, or Q equals CV multiplied by this extra piece. So these are the notes here for what they could be. So that is very, very fascinating. It takes us to this. I've written this out in class when I did this with you before. You have the Q equals CV, and we can figure this out here. When it's fully charged, it's coming up, and this E, this little E, is actually the time it takes to get to 63%. And I'm going to explain that to you soon as well. Okay, we'll get to that. But before we do get to that, let's understand that RC part. The RC, we already said that the resistor and the capacitor, the size of them will affect how long it takes to charge. So that means we can call that a time constant. If I take R and C and I know those two values, that is the time constant for the charge. The larger the value of R or C, the larger the time constant will be. So this is where we get into the, where did we get this 63% from? So as you know, we have this rule. Q final 1 minus E to the negative T over RC. The time constant, we know that is going to be the time takes to 63%, because when the time that you chose, let's say 10 seconds, ends up being the same as RC, which is tau. Remember, tau is a time constant, and let's say that it takes 10 seconds to get there. So kind of just cancel each other out, don't they? They'll just cancel each other out. So that means this is gone, and all we have is 1 minus E. So if I was to do E in the calculator, E to the negative 1, yeah, you will end up getting 0.37. That's like losing 37%. So 1 minus 0.37, as if this is 100%, minus 37%, that leaves us with 63%. That means at a certain point you will get to tau. This will be whatever my factor is compared to the R and the C. This is tau, and this always ends up being 63%. So it makes it easy to predict how much charge you will have if you do this to get to 63%. And later, because of the type of graph it is, you will realize that if you keep breaking this up, it will take 5 time constants to get to maximum charge. 1, 2, 3, 4, and then the 5. It's not very well spaced out, but this will be 5 time constants. That will tell us that we are finally reached the total charge possible. Okay. Charging current, a little bit different, because as we know, the current is reducing. So we can have your whatever the starting current is multiplied by, and you'll have just the E to the minus T, not the 1 minus, because I'm not doing 63%. We're losing it. So this over here, not there. I have lost 37%. This is only 37%. So it's the opposite of the other graph. So I've lost current here. So we just keep the E to the minus 1. Okay. If we know that I is V over R, the voltage, which is sometimes denoted as EMF, so we can just do V over R, and then you can do E to negative T over RC. So if you ever see this, this is for losing, discharging. If you see 1 minus this, that's for charging. Okay. So again, charging or discharging, we have to use these rules. For charging, 1 minus. For discharging, this. And the current is always decreasing anyway, so the current will always have this little piece at the end. If you want to find the maximum charge or the maximum current, we can use the normal formulas. Q equals CV, V equals IR, and that's it. Nothing crazy going on over there. So if you had a question that says you have a resistor and a capacitor in series with a battery and a switch, to find the time constant, you just multiply the two together. R times C, and you'll get your answer for the time constant. That's the time it will take to reach 63% of the charge. Okay. Another example you might get is if you have an uncharged capacitor in series to a battery, you have the battery voltage, you have the capacitance, you have the resistance. You switch it to A, which means the current will start to flow into the capacitor now. And you need to find the time constant, the maximum charge, the maximum current, and the charge as a current as a function of time. Time constant we've already done in the previous question, R times C, resistance times the capacitance. You just take these two numbers and you will multiply them. You will get 4 seconds. If you want to find the max charge, the maximum after an infinite time, usual formula, Q equals CV. We have the capacitance, we have the voltage, there's the V there, there's the C there. We will multiply them together. I is V over R. Again, we have the V, we have the R, we will have the maximum current. Okay, that should be, why is that a C? That should be an A. There we go. Okay. And now, this is the main part, which you need to find the charge as a function of time. So in order for us to do that, we can do Q equals whatever the maximum charge will be, and because it's charging, 1 minus e to the negative t over RC. So to make it as a function of time, we'll just put the numbers in that we know, and we'll just leave time there for now. The numbers that we know, the maximum charge possible, we've already calculated CV, 6 times 10 to the minus 3, so we will plug that in here. 1 minus e to the negative the time that we would be looking for over tau, which is 4. We've already calculated tau, RC. We've already done that. I can write 4. So now we can use this formula now to calculate the charge at any time. And it looks like we chose to check for 3 seconds. So we can substitute 3 seconds in here. So after 3 seconds, it will be this much charge. Which kind of makes sense because it's less, because we know at the time constant to get to 63%, we realize that the charge, we can figure it out by using 4 over 4. The number will be a bit different, but we're not going to get into that right now. So we figured out now that by changing this value of t will give us the charge at that second of time. Excellent. Discharging, again, same idea. We know what charging does. Discharging is the opposite. We use the same rule, T over tau, and like I mentioned, you have your time constants to reach the maximum charge, and the same, it's going to decrease. You're going to lose the time constants. It will take actually only 4 to get to the final. Well, not really 4, 5 here. This will be 5. 5 tau, or 5 time constants. There you go. So 5 time constants is needed to get to fully charged or fully discharged. Okay, so if you wanted to find the time constant, you have to see how long it will take to get to 63% of this. So you have to see from here, 63% of 5, figure it out, and you will see the time constant. Very easy, very nice. You might get a question which asks you to rearrange the formula to find the time taken. We did this example in class as well. If we have the initial current, and the capacitance as well. We have the capacitors connected to this resistor, the time taken for it to fall to the new current. So initial current, the new current, the resistance, the capacitance. So we have the rule, we're trying to find the current, so it's I, e to the minus t over RC, no 1 minus needed here. We have the final current that we're looking for, we have the initial current, no problem, multiplied by this. So we put the numbers in. Rearranging, take the 0.6 across, then you're left with this. If you remember, the opposite of this e minus here, opposite of this exponent, is the natural log, ln. So we'll take ln on this side. And that leaves us with just negative t over this number. Rearranging again to get t, and you will end up solving the rule, and you will get 0.1 seconds. So I've taken this to the other side. It becomes multiply, and of course it's negative, so I'll keep the negative there. And you get your answer, 0.1 seconds. And that's it.